So let me say hello. Glad to see all of you. I'm very happy to be here. This is actually the first hackathon that I've been to.
Really?
Looks
Welcome.
like. Thank you. So this one I call A Tale of Two Systems, and it's about it actually comes from a post that I've written online. I've gotten a couple of posts up there, and when they asked me to talk, I said, here, why don't you look at the various things that I posted, and this was one of the ones, the story that they suggested. So let me say just a little bit of where I come from. I work at LinkedIn. So this is a picture from inside the LinkedIn office. We're located inside the Empire State Building. A lot of people don't know about the R&D that we have in New York, but we do actually have a sizable group, and those are the teams that we have represented in the office. And I'm a member of the content ingestion team. And what we're about is when you get onto LinkedIn and you paste the URL into the update to share an article with your connections. A little panel pops up with a little thumbnail of the article and the title and the link to click on, and we're the back-end system that goes out and scrapes all the URLs that people want to share. And so this is a little bit about me. I've been working as a developer for about the last year and a half at LinkedIn, but I've been a developer for many years before that. The overall message of what I wanted to talk about, so we start with the idea that we're all aspire to be better developers, and then the question is, how do you go about becoming that better developer, that master builder? I got this analogy from George Fairbanks, who wrote this. He works at Google in New York, and he wrote a book about software architecture. And he says, what's the difference between someone who is a real master builder? And he says this is an analogy to imagine that you're in this scenario that there's a football game going on, and a rookie football player is watching the football game, and a coach is sitting there watching the football game. And so the question is the rookie and the coach watching a football game, are they really seeing the same thing? So on some level, they're both looking at exactly the same thing, but the coach, having had this experience and maybe studied the game and knowing a lot about how football works, understands it a little bit better. We're going to watch a play. It takes only about 7 seconds to see. So I have a question for you. I'm going to roll it back to the beginning. You all just saw that. Ball. How many of you think you're pretty sure that you know which is the one who caught the ball? Okay, so like one hand. Now let's watch it again. Okay, how many of you were right? Okay, so we got the two hands. Now how many of you think you know who caught the ball? Okay, so we have a couple more hands. This might help. Now, what this idea is about is, so first of all, you see that it's not always easy on the first glance to see what's really going on, and it takes sometimes a couple of repetitions to see the pattern of what's going on, and that if there's somebody who already has seen this a few times, if they draw that little line on the screen for you, that sometimes that can make all the difference in the world between being confused and getting a better insight. Who, the coach or the rookie, would be better placed to answer a kind of question of what kind of offensive play was that? Who was the one who was out of position? Even though you see the same things, because you have this understanding, this conceptual framework of how the game works, you understand better what it is that you're looking at. So now let's go away from football and let's put on our coach's cap and look at some software. So this is about a tale of two systems. A couple of things to understand. This is a credit risk system. It means that the purpose of the system is every night we compute how much risk there is to the bank. And it's not important to understand exactly how that is done, except to know that there is millions of trades that form the input, and for each trade we compute this fixed size block, which is actually pretty sizable, half a meg of data. And then what we have to do is we have to combine all of these together to get a total picture of the risk. And this is what the system kind of looked like. What you have is you have input files. There's some processing goes on that makes these risk matrices, and then we write to the output. And what I'm showing there with the lines is that some of them are blue, some of them are green, and in the output file, all the blue ones, wherever they're coming from, and all of the inputs, they all get combined into one output. All of those matrices get combined together. So how did they build a system that would do that? It kind of looked like this. You have a distributor which takes these trades and it sends them out to this big grid of computers that compute all these risk matrices, these fixed size half megabyte chunks of data, sends them all over to that aggregator thing, which is one machine, and that aggregator then writes that output file into the disk. And the problem that they were having was basically this, that the aggregator was getting overwhelmed with the data, and then need to figure out, okay, what exactly is going on, what is getting overwhelmed. Look at the system, and you see that the system is quitting in the middle of running with an out of memory error, and it's mainly happening when it's processing the largest input files. The next clue we have is that we look to see, well, we must be running out of memory, but the task manager says we have lots of memory left. You shouldn't be throwing out of memory errors. It seems like everything should be okay. So look a little more closely. Where is the failed memory allocation happening? And we see that there's one place in the program where somebody is asking for a huge chunk of data, well over half a gigabyte of data, and it's not able to get it. And therefore, since it can't get it, the program quits. And the question is, why couldn't it get half a gigabyte of data, even though there seemed to be that much free memory left? And the answer is that because the address space of the process has been used and memory has been allocated free, there's lots of chunks of data, lots of chunks of space that are available, but there's no chunk big enough left that can serve that huge request that's being made. So the first question people asked is, who heck needs that much data all at once? What in the world is the program doing with it, and what can we do to fix it so that our program is not blowing up? It was still running in a 32-bit world, and 32 bits gives you this total address space of 4 gigabytes. But from the process's point of view that's running, it thinks that it has 2 gigabytes for itself and 2 gigabytes for the operating system. What the system was doing was it was using this virtual memory system to open a file, and it opened a file using a memory mapped file. So how many of you have heard the term memory mapped file before? Familiar with what that is? Okay, so just a little bit. So the idea of a memory mapped file is that you take a chunk of space on a disk and you pretend that that's memory that you can write to. And every time you make a change, all this memory management unit hardware that's in the system is optimized to immediately know when you've changed something, when what's on disk is different from what's in memory, and it'll learn to flush it out to disk. It's an extremely fast way to write, and accessing it is as simple from the programmer's point of view as accessing an array of data. Let's put our coach's cap on and say, what can we learn from this? So the first thing is that when your system is blowing up, it may already be too late. You don't want to wait so everything is in crisis mode before reacting to something. The other thing you notice is that the actual problem is not that the machine was underpowered. You can't always just buy a bigger computer. Sometimes you have to do something else to change it. This fellow, Tom Gilb, had a good way of saying that you have to proactively look for risks to your system, because if you're not paying attention, one of them is going to sneak up on you and get you before you have a chance to react. So this is what they decided to do to address this system. They said, look, this whole memory mapped file thing has been good now for our little system, but our system is outgrowing this. So let's do something else which is they picked a product that's an in-memory distributed data cache. And what that means is that instead of writing to the computer's local disk, you write instead to this cluster of computers. And what they do is they're not even about writing to disk. They just hold all the data that you want in their memory. And when they have some spare time, they'll write it to disk so that you have a backup copy and it's safe in case the power goes out or something like that. But you have all these computers that have shared amongst them in their memory all the data that you need, and then when any one of those client computers asks for the data, they'll just give it to them. They said this is a great system because now it's not all relying on that one aggregator computer to store the data. Now you have this big cluster, and the system has all sorts of other nice features to it. It's considered to be fast. It's fault tolerant. This means one of the units in the cluster can go down and it won't lose any data. It'll still be able to recover. And if you ever outgrow it, you just add more computers to the cluster. This seems to be a system that they need. The system is available in several different sizes, so you can start off with a small version, and as you need to grow, you can grow to the big version. So they set about changing the system to use this new in-memory data cache. And developers were not entirely happy about this change because this was way more complicated. The old system was just like accessing memory, and now you had this whole API for how you can read and write. Is much more complicated to set up. When you try to test it on your desktop, if you don't have this whole cluster available to you as a developer, there's one shared between all the team, and maybe the one that you have in the test system is not exactly the same as the one in production. So it's a whole bigger headache to test. And when you try to write your code, you find that there are all these different constraints that the code requires you to follow in order to use the new system that you didn't have to follow before. And after you've done all this work to get it to work with the new cluster, you haven't actually added anything new function-wise to the system. All you've done is solved your immediate problem of, oh, my system breaks down when the input gets too big. But on the other hand, it had some good features. At least it's going to fix our scaling problem, the developers said to themselves. They also said that, well, once we have this new system and growth is not a problem, we could perhaps add all sorts of new features that we couldn't have done before because we were restricted on the growth. And also, they knew that they were buying some pretty expensive machines to run to run the in-memory cluster. It was much more powerful than the aggregator machine that it was replacing. So they figured, well, and at least everything else, the system ought to be faster. So once again, this is the old system, and what they did was they changed to the new system by tacking on the spiffy new distributed in-memory cache, which you can't quite read there because it's on the bottom there. But as soon as they started running the new system, they did some timing on the system, and they found that the new system was significantly slower than the old system. And they're thinking, like, we just did all this work, and it's all slower. What did we do all this work for? And after scratching heads for a while and maybe contemplating a little finger pointing and a little bit of panicking, as I put it in the story, the one person who kind of looked at all this and said, and it wasn't me. I'm just the one who was observing this. And his observation was, of course it's slower. And okay, why? Why is it slower? So it comes down to when you replace a fast connection to an internal hard drive, and you replace it to writing to something over a network connection, to something that's in another computer, it's always going to be slower because the data path to the disk is so much faster on a local computer than it is going to any other computer. And so what you notice is that the old system was actually tuned quite well to be high performance. But the problem is that you had a problem of scalability. It wasn't going to be able to handle the input that you were giving it. And so therefore you had to make a move to redesign something to improve its scalability. When you do something to improve scalability for something that's optimized for performance, the result is not going to be optimized for performance anymore. The old system, they knew that they had a single aggregator machine, and so what they did was they very carefully configured the system to make sure that they never exceeded the capacity of that machine. So for example, all those red connections coming in, what if you had wanted to have, instead of, as I showed, 9 computers there, what if you wanted to have 90 computers all doing work and sending stuff to the aggregator? Well, it's only a single machine, and that single machine can only handle so much data coming into it at once. So they always made sure that the amount of data coming into that machine was something that one machine could handle. Ultimately, the system was only fast because they were very careful to never break it in any way that would make it be slow or break. And so what they really gained from the system was, yes, sure, the new system is slower than the old system, but what if your input gets even bigger than you tested before? What happens to the runtime of the old system? Well, you get basically this. The new system has the big advantage of the old system is that it doesn't die when the input gets too big. That is really important. That was why you undertook this work in the first place. So it comes down to something like you have to compare sort of apples to apples, or you have to understand what is the proper way to look at what's important to you, what are the most important attributes of the system. And the other thing to keep in mind is, again, that the system was fast because they, over time, always made sure that the work would fit the system. And whenever somebody had an idea for, hey, there's something I would like to do different, if it didn't fit the current system, they would automatically say no. So let's go back to this new system and see. If you notice here, there's still only one machine over here. Everything that you're writing to over here still goes through here. And so everything that goes through here is no faster than it was before. It's exactly the same. The only thing that you've done is made this part slower. And even though this can handle more, you still can't push any more data into here than you can fit through here. One thing you might think of doing is don't have a single aggregator. Put whatever some of that aggregation function into each of those workers and have them each contact the cluster directly. It's a multi-machine cluster for a reason, and the reason is that you can make a connection to any one of those machines and save data or read data from any one of those machines, and it scales because you can add more machines to that. Also, remember I said about how you had the records of the same color all need to end up in the same place? So one of the things about in-memory distributed caches is that if somebody writes a blue record over here, and also somebody writes a blue record over here, these two things now need to sync up. And so behind the scenes, these things are all talking to each other, saying, hey, somebody just updated data over here. All of your copies are wrong. You need to get me the new copies. So you could think of doing some partitioning on the data and say, okay, you're going to have the distributor say, okay, you bit of workers, you get all the blue ones, you get all the green ones, and now there's much less interaction that has to happen on the distributed cache. All those machines can really run independently almost, would not have to constantly exchange data to sync up. And once you've done that, you could say, well, the other thing is I don't have a single machine anymore. I could make that grid a whole lot bigger, and I could produce data a whole lot faster, and I could just pump more data into that distributed cache much faster than I could, and certainly still having that single aggregator in the path would have never enabled you to be able to add workers like this. So what makes this kind of an interesting example that you can learn from is that the old architecture and the new architecture, you changed something, you changed the architecture, but in terms of features that you change, you haven't actually changed any features of the program. The program still does, function-wise, exactly what it did before. So let's look a little bit. So the old architecture, it had certain advantages. Memory map files are really fast. Reading and writing from the programmer's standpoint is as simple as dereferencing a pointer. And it's already done, which means you don't have to write anything to make it work. But and on the other side, for the new architecture, you have some minuses in that it's slower. But if you look at it from, and more complicated API, okay, and creates undercode. I already said all that before. But there's some drawbacks to the old architecture, which maybe you didn't focus on as much when you were using it. The first thing you noticed was that you can't fit anything bigger than can fit into one process. That was the trigger that made you need to fix this. But you didn't pay much attention to the fact that having a single distributor and having a single aggregator meant that if that computer breaks, then your whole system can't function. You have a single point of failure, or if a bug causes the program to crash somewhere in the middle, you lose all the work that you've done because everything is forced to go through a single machine. You have the networks are all the network connections are converging on one machine. The maximum data that you can do, it depends on how much data you can push through a single machine. And if you wanted to fix that problem and add scaling to the old system, it would have made a lot of changes that you would have had to do. And you probably would have found that whatever you came up with would have made the new system slower no matter what you did. And on the other hand, the new architecture, it can handle the larger output. It has fault tolerance now. Now you don't have to worry about what happens if one machine goes down. It has a scalable cluster, which means you have a path to growth that doesn't involve lots of code changes. You can write your code once, and you can continue to scale it up without having to rewrite the code every time. So what is a coachable moment from this? That scalability is a trade-off. And it's not just true about scalability. It's true about every kind of attribute that you want to have in your system. And really, software engineering is all about trying to see what those trade-offs are and then picking what's the best balance for whatever it is that the system is that you're trying to build. This also highlights something about changing an architecture, which is that trying to rewrite a program to work in an entirely different way, that's often the hardest thing that you can do to a program. But making a change like this often involves rewriting bits of the whole system. Every little part that accesses that pointer that was supposed to go straight to that memory mapped file now has to go through a whole different code path and may have very significant implications for how you have to change your code. It also is interesting in that it isn't an attribute like scalability. If I looked at the code before and I looked at the code afterwards and I wanted to say, well, can you point to me to the new scalability code that I added to? Scalability or reliability or performance, these aren't things that are features that are found in the code in exactly the same way as actual features that do functionality are. And in some ways, there's somewhat higher level attributes that are rather a description of a way to differentiate a feature from a quality attribute is a feature or functionality tells you what your program does, and a quality attribute tells you how your program is. Okay, so having looked at this system and learned a lesson to it, now let's go and win a Super Bowl. Yeah?
Is this part of a specific software testing or software development lifecycle?
There is a way of the idea of quality attributes. First of all, is there anyone who's familiar with that term? Has anyone heard that term quality attributes before? Has anyone heard the term functional requirements before? Yeah. I'm just curious. So for people here who've taken like computer science curriculum, stuff like that, how many of you have taken an actual class that's software engineering? Like not just okay, so just a couple of you. When I took software engineering, we used to in that class we talked about functional specifications, which were again the things that your computer program needs to do, and then there were these things like and I needed to have uptime of such and such, and I needed to be able to if I need to change the database, I want to be able to say that I could change the back-end database, and it wouldn't take a whole lot of work to do, and I'd make a separation there. And these were referred to sometimes as non-functional attributes. Have you heard that? Did you hear that term in your class, non-functional attributes? So I learned from George Fairbanks. He said that he personally doesn't like that use of the term, because if you were to go and be in a park and see a water fountain and it had a label on it that said non-functional, the first thing you wouldn't think of is that that must be extremely reliable or scalable or high performance. You'd think it's broken. So that's not the intended connotation. The connotation means that it's an attribute of the system that isn't about what it does, but more about what it is or qualities that it has. And so there's actually a process that I also did a talk on that at one time called that's actually specifically about, it's not about coding, as a whole methodology for getting all the stakeholders together, discussing out what are the priority orders of the different attributes that you want, what things trade off with what, like what things you need to give up in order to get something that you want, and then are you willing to give it up, and then saying, okay, here are some architectural ways of addressing the list of priorities that we've actually come up with.